Chapter 8, Problem 104, by me, Melissa Seib. A 20 kilogram object is acted on by a conservative force given by F equals negative 3x minus 5x squared, with force in newtons and x in meters. Take the potential energy associated with the force to be 0 when the object is at x equals 0 meters. Our givens are a mass of 20 kilograms, a force equation given above, a potential energy of 0 joules at x equals 0 meters. Part A asks us, what is the potential energy of the system associated with the force when the object is at x equals 2 meters? We're going to use the equation force is equal to the negative derivative of the potential energy. We'll rearrange to solve for potential energy and take the negative integral of the force function. We'll then evaluate it from 0 to 2. We'll find that 3 halves x squared plus 5 thirds x to the third, and then we'll evaluate it from 2 to 0, plug in, and solve to get 58 over 3 joules of potential energy from 0 to 2. Because at x equals 0 we have 0 potential energy, the change in potential energy from 0 to 2 will be equal to the potential energy at x equals 2. Therefore, potential energy of x equals 2 is equal to 58 over 3, which is about 19 joules. Part B asks us, if the object has a velocity of 4 meters per second in the negative direction of the x-axis when it is at x equals 5 meters, what is its speed when it passes through the origin? We're going to use the same equation again. F of x is equal to the negative derivative of potential energy. Our givens are given in the top right corner. We'll rearrange to solve for potential energy once again and take the negative definite integral of the force function evaluated from 0 to 5. 3 halves x squared plus 5 thirds x to the third, evaluated from 5 to 0, plugged in, and solved to find 245.83 joules of energy of potential energy from 0 to 5, because once again we know the potential energy at x equals 0 is 0. The change in potential energy from 0 to 5 must also be the potential energy at x equals 5, and so we know that the potential energy at x equals 5 is 245.83 joules. Next, we're going to solve for the kinetic energy using k equal to 1/2 mv squared. We'll plug in our givens, a mass of 20 kilograms, a velocity of negative 4 meters per second squared, meters per second, and find that kinetic energy at x equals 5 meters is 160 joules. The total mechanical energy in the system is the kinetic energy plus the potential energy. We'll plug in our kinetic energy at x equals 5, which is 160, add it to our potential energy at x equals 5, which is 245.83, to get a total mechanical energy of 405.83 joules. We can then plug these back in to find the kinetic energy at x equals 0. Because our total mechanical energy is 405.83, and we know at x equals 0 our potential energy is 0, our kinetic energy at x equals 0 is 405.83 joules. Using the same equation again, k equal to 1/2 mv squared, we'll rearrange it to solve for v, plug in our k at x equals 0, which is 405.83, plug in our mass of 20 kilograms, and solve to get a velocity of 6.4 meters per second. Part C, the first half, asks us what the potential energy of the system associated with the force when the object is at x equals 2 meters if the potential energy at the system at x equals 0 is negative 8 joules. Essentially the same question as part A, except at x equals 0 we have a potential energy of negative 8 joules, not 0 joules. We'll use the same equation we used in part A, f of x is equal to the negative derivative of potential energy, rearrange to solve for potential energy, and this time we'll take the indefinite integral, negative integral of the force function, and to get 3 halves x squared plus 5 thirds x to the third plus c. Because we know at x equals 0 we have a potential energy of negative 8 joules, we'll plug in 0 for x, set it equal to negative 8 joules, and get a value of negative 8 joules for c. We can use that new equation for potential energy, plug in 2 for x, and get a potential energy of at x equal 2 of about 11 joules. The second half of part C asks us what part B asked us, except this time for a negative 8 joules of potential energy at x equals 0. So we'll use the equation we found for potential energy in the first half of part C, which is potential energy equal to 3 halves x squared plus 5/3 x to the third minus 8. We'll plug in for x equals 5 to get a potential energy of 237.83 joules. Then we'll solve for the kinetic energy at x equals 5. Using k equals 1/2 mv squared, plug in our mass of 20, our velocity of negative 4 to once again get 160 joules. Then our total mechanical energy is equal to the kinetic plus the potential. We'll plug in 160 joules, which is our kinetic energy at x equals 5, plus 237.83 joules, which is our potential energy at x equals 5, to get a total mechanical energy in the system of 397.83 joules. Plug this back into that equation to solve for the kinetic energy at x equals 0, and we'll get 397.83 joules is equal to the kinetic energy at x equals 0 plus the potential energy at x equals 0, which we know in this case to be negative 8 joules. Add 8 to both sides to get a kinetic energy at x equals 0 of 405.83 joules. Plug right back in to kinetic energy equal to 1/2 mv squared, which you've rearranged to solve for velocity, and you'll once again get a velocity at the origin of 6.4 meters per second.